Mm. Hello everyone. Am I audible?
Hello, hello. Good evening. Yes, you're audible.
Yes, you're audible.
Okay. So uh, I'm Roshan. I'll be your teaching assistant for the starting from week 9. Okay. All the topics related to GNNs, node embedding, edge embedding, and so on. Okay. And yeah, I'll just briefly summarize the topics that were taught during week 9. And then if you have any questions in any of those, you can let me know. Okay, this will work, right?
Yes, yes.
Okay,
Yes,
I'll share my screen now. Yeah, I hope my screen is visible. Okay,
yes, it's
so I hope you're all familiar with what a graph is, what are nodes and edges, and so on. And so you have regarding node embeddings, the objective here is to compress this graph, okay, uh, or map it to an embedding domain. Okay, so that so if you talk about node embeddings, you have a vector associated with each node. Okay, and the properties of these vectors in the embedding domain is that when these, let's say you and we are adjacent in this graph, the corresponding embedding vectors are also close to each other in the embedding domain. So that's what it's written here. Distance between embeddings reflect the positions of nodes in the graph. If it's far apart in the graph, if two nodes are far apart, the embedding vectors will also be far apart. Okay, and applications wise, it can be used to any network in biology like PPI, gene regulatory networks, and so on. Okay, so these are some mathematical notations. Okay. And yeah, can anyone let me know what an encoder or decoder does and why do we need it here actually?
to reduce dimensionality.
It's not about, okay, reducing dimensionality of what?
Of the input vector that contains the graph.
Mm, I think you're, no, no, no. So encoder is, is something that transforms the graph, okay, and maps each node to a low dimensional latent vector. And what would be the size or shape of this matrix? Anyone? Size of this matrix, shape of this matrix. So how many rows it will contain for any arbitrary graph? That will be equal to your number of nodes, right? And the columns, that will be decided by you, the number of columns. Okay, that is something that you have to fix beforehand and then do this whole encoder and decoder thing. Okay, so this is how it works, where an encoder function, you have an encoder function for each node in the graph that will correspond, that will map it to the corresponding d-dimensional vector. Okay, and yeah, how do you actually use this similarity function is you have two adjacent nodes in the graph and you get the let's say maybe the corresponding elements in your adjacency matrix. Okay. So if ST of U and V is 1, the similarity score is 1, what does it actually mean? The nodes U and V are actually adjacent to each other. Okay. Since the similarity function is based on the adjacency matrix here in this case. Okay.
which means they are directly connected.
Yes. Yeah.
Okay.
Moving on to the decoder part. So decoder does the opposite. Given two latent vectors ZU and ZV, okay, it actually tries to reconstruct the similarity score between those two nodes. Okay. So here, if you give a d-dimensional latent vector for U and V, what it outputs uh, is the similarity score. Okay. And in the end, what you calculate is something called the loss function. So the encoder will give a d-dimensional latent vector for each node. Okay. And the decoder takes in two d-dimensional latent vectors and tries to reconstruct the similarity score. Okay. So this particular part, okay, this is the reconstructed similarity score and this is the original similarity score. And you define something called a loss function or objective function so that the approximated similarity score is actually equal to the original similarity score. Okay, and this is how you update the parameters in the encoder and decoder function. Uh, any any doubts in this part? Like, why do we need an encoder and decoder, or do you need any further explanations?
Could you explain this once more, please?
Okay, so encoder takes in the node or node ID as input and outputs a d-dimensional vector. Okay, that is what this part is. Okay, that is clear, right?
Yes, yes.
Okay, so you also have a similarity score. Okay, that also takes in two node IDs as input. Okay, and what essentially you want to do is try to get parameters for these functions, the function encoder and function decoder, so that the reconstructed similarity score is equal to the original similarity score. So same concept here. Yeah, nodes that are close to each other are also should also be closer in the embedding domain. Okay, so the same principle applies here in this case also. The approximated one or reconstructed one should be equal to the original similarity score. Okay. Any more doubts?
No, I got it.
Okay. Yeah. So this is okay. Uh, and what you do is you optimize the parameters in your encoder and decoder such that this loss function is minimized. Okay. Whatever you get from the embedding should also be equal to the true similarity. So you want the loss function to be minimized. Okay. So for each pair of nodes in your data set, you calculate the estimated similarity, you calculate the true similarity, and try to minimize this loss. Okay. The ideal loss value here would be 0. Okay. And the minimization can be done using any optimizer. So stochastic gradient descent is one. Okay. Or also you can also try to use matrix decomposition, SVD. Okay. So this is how it looks Okay, the overall goal. Okay, so you have an encoder function that transforms U to ZU. You have another encoder function that transforms V to ZB. Okay, and these functions you have to define beforehand. Okay, and the similarity is defined like this. Okay, this is my similarity function for estimated similarity. This value should be equal to the entry in your, or let's say your similarity function that you use is the adjacency matrix. So this value that you calculate should be equal to 1 or 0. And yeah, so you map each node to a d-dimensional vector. So this is how Z, the Z matrix actually looks like. The each row represents a node in the graph, and the column here represents the size of the latent vector. Okay, so you encode each node and decode the neighborhood using the decoder function. Uh, so I think this is how we store the embeddings. Like I explained before, each row corresponds to a node, and the columns correspond to each element in your d-dimensional vector. Okay, and you get the similarity by using the dot product. Okay, so this is, so for each node, so it's represented by the specific notation. And finally, for a graph containing B nodes and E edges, okay, this is the matrix, embedding matrix. Okay, and yeah, so how do we get these embeddings? Is uh, so there are different methods of getting these embeddings. Okay, and before this, I think you were all familiar with these vector operations. This is how you calculate the L1 norm, L2 norm, and so on. This is quite simple. You can actually go through it. Okay. And yeah, I think moving on to matrix factorization. Matrix factorization is an approach where you split certain matrix into two or three lower dimensional matrices. Okay. And the first thing that we can look at is something called singular value decomposition, where you split matrix A into three smaller matrices, okay, U, D, and B. And how do you actually uh, just so after getting these three matrices, how do you actually convert it into a lower dimensional form? Anyone has any idea how do we actually do it?
We had learned this earlier, but
Okay. So what you do is once you get the U, D, and V matrices, let's say if you want to reduce it to specific dimension K, okay? So you only take K columns from each of these matrices, then multiply it, okay, and you get the reduced form of A, I would say reconstruction. That will be of dimension n cross K. Okay, so this is essentially like your dimensionality reduction. Okay, I hope this is good. Okay, so you just take K columns from each of these matrices, multiply it the same way, and you get the reduced uh, representation of the original matrix A. Okay, and the shape of the matrix will be n cross K. Okay, just put there. Mhm. Okay, yeah. So I think most of the other approaches are also somewhat similar to the SPD case, where instead of actually going to the analytical form, you just convert it to an optimization problem and then determine the parameters accordingly. Okay. And yeah, it's all based on the loss functions here. So basically, I think there'll be a table where it explains each approach. Okay. So there are different methods of getting these embeddings. How they differ from each other is the decoder function that you define, the similarity measure. The similarity measure can be the Laplacian matrix, that is your degree matrix minus your adjacency matrix, and how you formulate the loss function. Okay, so all these methods use different ways of constructing the decoder similarity measure and so on. You just need to know what is uh, different, the decoder similarity measure and the loss function. Most of the times, the loss function will just be the mean squared error between the estimated similarity and the true similarity. But yeah, other than that, it's fine. This is again a visualization of how you do SPD so that you get the matrix. Okay, with the reduced dimensionality. Okay. Mm, yeah. Any other doubts? Although all these might have different, I would say, a lot of mathematical formulations, you just need to remember what is your decoder, what is your similarity measure being used, and what's the corresponding loss function. You don't need to worry about how to do the optimization and update the parameters and so on. Okay, that is in itself a very separate topic. How to do the optimization, like how to use SGD and so on. Okay, but you just need to know how the objective function is determined. Okay, and all the objective functions will again come back to this specific principle only. If they are close here, they should also be close here. Okay, that is how you define the loss function, similarity measure, and decoder based on the same principle but different variants. That's the only difference. Any doubts in this specific part? I can explain anything in detail if you want. Any concept from these sites.
Right now, can't think of a doubt, but while solving problems, may come across some doubts. So maybe flag the group. Yeah.
Okay. Okay. Not done. Okay. Place on the call. That is fine. Mhm. Okay. So anyone can, so those who have gone through the lectures, can anyone explain what random walk embedding means and what's the difference between the existing factorization based methods? Anyone? Okay. So here, random walk embeddings. See, the previous matrix factorization based approach, everything is, I would say, deterministic. Okay, you'll get the same matrices. Again, you use a similarity function, okay, that is similar to the adjacency matrix. Okay, the embedding should be optimized to satisfy the specific criteria and so on. But here in the random walk based approach, it's a very stochastic measure based on probabilities. Stochastic, I would say, um, let me just, it's stochastic, I would say, like each time you run the random walk algorithm, I would say the embeddings also might differ. But how many times you do the factorization based methods, you'll get the same d-dimensional vector. Okay, I would not say that these methods, whenever you run it again and again, you might get drastically different latent vectors, but they do change quite a bit. Okay, so that's why it's stochastic. It's as the name suggests, it's random. So how do we do the random walk embedding? Is you start with a specific node, u. Okay, you take a random walk around this graph. You specify a walk length. Okay, and you specify how many random walks you need to do. So you have to specify these two things beforehand. So these are different possible random walks of length 2. So I go from u to x, x to w. Okay. I can go from u to v, v to w. I can go to u to x, x to w. Okay. And I store all these values. Okay. xw, vw, xv, and so on. Okay. And so how after getting all these random walks for all your nodes, what you can get an idea, you can get an idea of how close the nodes are to, let's say, the specific node u here. Okay, if x occurs more times in the random walk sequence that you have generated, that is more closer to you than, let's say, w. Okay, in the factorization based methods, you assign it a value of 1 since it's connected, directly connected. Okay, but here it's probabilistic, so you might assign a probability of value of, let's say, zero point 0.9 or 0.95 and so on. Okay, so the first thing you have to uh, do here is, I'll just show the- yeah, summary. Okay, you simulate random walks of length t from each node. Okay, and you can repeat it how many ever times you want. Okay, again, the random walk of the walk length and the number of times you can run the random walk algorithm is, I would call, as an hyperparameter. Okay, so I mean, you should determine which is your best walk length and how many random walks you have to do for each node based on a downstream task. The downstream task can again be a node classification task, a link prediction task, and so on. Okay, based on the downstream performance, you can change the walk length and the number of random walks that you can do. Okay, and again you have a loss function. Okay, that is defined like this. Okay, and you want to minimize this loss function. And again, there is a decoder function that is defined like this. So every algorithm has those three components: a decoder function, a similarity measure. The similarity measure here is obtained from the random box that you generate, and you also have the decoder function, how different it is. Okay, and based on how the decoder function handles the specific denominator term. Okay, if you sum over all the combinations of nodes, this is actually a very computationally expensive operation. Okay, so deep walk and node to vec, they use different approaches. One is called the hierarchical softmax. The other one is the noise contrastive approach. I mean, you don't need to go into the details of how the hierarchical softmax and noise contrastive approach work, but just remember I would say it's better if you just know the decoder function. Why is this operation very expensive to do? Okay, so yeah, you have deep walk and node to vec. Okay, even though the decoder function is same across deep walk and node to vec, how this calculator that uh, determines, that's the difference between these two algorithms basically. Okay? And we have done a case study between all these two, how the embedding size actually uh, determine the downstream performance and so on. I think, yeah. Again, it's the edge embedding. For each pair of each edge, you have a corresponding representation. And how you can get edge embedding is you can either take the average of u and, let's say if you want to get an embedding for, let's say, this specific edge u and x, okay, you can take the average, you can do weighted L1 or weighted L2, and these are the different kinds of operator for notepads that you can use. Okay, these are uh, simpler approaches. There are more complex approaches than just taking the average weighted L1, weighted L2, and so on. Okay, and again, we have done a comparison between the embedding size, the downstream model, and so on. Uh, I know the algorithms described here might be a little bit difficult to understand, but if you go through the coding tutorial or if you try to do exercises, I would say it would become more easier. Okay. Mm, yeah. Any questions? Uh,
Haven't yet tried the coding, so
okay. Okay. Yeah. If you have any doubts, you can ask now. If you don't have any doubts, we can end the session here. And yeah, you can ask the doubts next week also if you have gone through the coding notebooks. So yeah,
okay.
yeah. Thank you.
Yeah, thanks for the session. Bye.
So thank you.